You sit down, you turn on your computer, and the screen is just completely black.
Oh, yeah. The absolute worst feeling.
Right. Your heart just drops. You immediately assume your expensive hardware is dead, your productivity for the day is totally ruined, and, you are just entirely cut off from the digital world. But today, we're going to show you why your monitor is, well, usually lying to you.
It's a very specific type of modern anxiety, I think. Because the display itself is it's a black box for most people.
Totally.
When it fails, the instinct is just catastrophic hardware death. But the reality is often much more nuanced and honestly usually much easier to fix if you just understand the underlying mechanics of what's happening.
Exactly. So, today's deep dive is jumping into the world of CompTIA plus display troubleshooting, and we're drawing specifically from Professor Messer's curriculum.
Yeah, excellent material.
It really is. But our mission today isn't just to help you memorize facts for an IT certification exam. We want to turn you, the listener, into a confident display detective.
I like that display detective.
Right. We're going to cure that information overload with practical, real-world logic. We want you to understand the actual why behind these tech failures.
Yeah.
So, okay, let's unpack this. And let's start with the most abrupt and terrifying failure of all total darkness.
The dreaded black screen. It really is the ultimate roadblock because it removes your ability to interact with the system entirely.
Look, for an IT professional taking this exam, or even just, someone helping a coworker out, telling a user to check the plug feels like a really good way to get yelled at.
Oh, for sure. People hate hearing that.
It sounds so patronizing. So, I want to compare it to a car that won't start. The instinct is to assume the engine is dead, but obviously the logical first step is checking if there's gas in the tank. Is asking someone to check if the monitor is plugged in actually mathematically necessary, or is it just that cliche IT support script we've all heard a million times?
No, it is absolutely mathematically necessary, and it's entirely based on the physical realities of data transmission.
Okay, how so?
Well, it isn't just about whether the monitor has electricity flowing from the wall, although, obviously that's step one.
Right. Kind of important.
Exactly. But it's really about the data path. Modern display cables, so like HDMI or DisplayPort, they have multiple microscopic pins inside the connector. Some of those pins carry the actual video signal, but others carry something called EDID.
EDID.
Yeah, it stands for Extended Display Identification Data.
Okay, so what does that actually do? It sounds like the cable is actually having a conversation with the computer, not just acting as a dumb pipe.
Precisely. The EDID is essentially the monitor's resume.
Oh, wow.
Yeah, it tells the graphics card, hey, I'm a Dell monitor, here's my exact native resolution, and here are the refresh rates I can handle.
Ah.
So if gravity or, a foot brushing against a cord under a desk dislodges that connector even a fraction of a millimeter.
It drops the connection.
Right. The pins carrying that EDID handshake might lose contact. The monitor still has power. The light on the bezel might even be on, but the computer physically cannot see what is attached to it, so it sends no image.
Okay. That reframes it completely. It's not about accusing someone of not knowing how a wall outlet works.
Yeah.
It's about verifying that microscopic data handshake.
Exactly.
But let's say that handshake is solid. Everything is plugged in securely, pushed in all the way. The screen is still totally black. The material talks about how auto detection can fail. Walk us through the mechanism there.
Yeah, so this is a great example of smart technology creating its own problems.
Yeah.
Monitors today are manufactured with multiple inputs to be versatile.
Right, you've got HDMI, DisplayPort, maybe an old VGA port in there.
Exactly. And they are programmed with firmware that constantly scans those ports, looking for voltage that indicates a live signal. But that auto-detection polling algorithm isn't flawless.
It gets confused.
Very easily. Sometimes the internal logic board gets tripped up by residual voltage, or it just stubbornly locks onto the last port that was used, even if you just remove that cable.
Oh, I've had that happen.
Yeah. You have this beautiful live data stream coming in on HDMI 1, but the monitor is just staring blankly at an empty display port. You literally have to use the physical buttons on the monitor to manually force the logic board to switch its active channel.
So the screen isn't dead, it's just looking in the wrong direction.
Exactly.
Okay, let's explore a scenario from the sources that I think is uniquely frustrating. I call it the Windows splash screen tease.
Oh, I know exactly where you're going with this.
You press the power button on the computer, you see the manufacturer logo, you see the Windows loading icon spinning, you feel total relief, and then suddenly, black screen. The monitor acts like it's dead.
Yeah.
What is happening during that specific transition?
That is a classic handoff failure. It's a failure between two completely different software environments. When you first hit the power button, your operating system, like Windows, isn't running yet. What you are seeing initially is the computer's motherboard executing its basic input-output system, the BIOS.
Okay.
And the BIOS is designed for maximum compatibility. It outputs a very low-resolution, incredibly basic display signal that every single monitor logic board on Earth is programmed to understand.
So the BIOS is essentially using baby talk to guarantee the monitor can hear it.
That's a perfect way to describe it, yes. But the moment that Windows loading screen finishes, the operating system takes over the hardware. Windows stops using that universal baby talk and attempts to load its specific, highly complex graphics drivers.
And if those drivers are broken?
If they're corrupted or if they have been misconfigured to push a resolution or a refresh rate that exceeds the physical limitations of your specific monitor, the monitor's protective circuitry just kicks in.
Contradict itself.
Right. It realizes it cannot parse the incoming data stream, and it shuts the display down to prevent hardware damage.
Which leaves you in a terrible position. Because how do you fix a setting in Windows if you can't even see Windows to click on the control panel? You're flying totally blind.
You are. But the source material provides the ultimate safety net for this exact paradox. It's the F8 key, or, the modern Windows equivalent of booting into safe mode.
Right.
If you interrupt the boot sequence, you can force Windows into something called VGA mode, which is a low-resolution video mode.
Wait, isn't VGA a totally obsolete analog standard from, the 1990s? Why is a modern Windows 11 system still relying on that?
Because backwards compatibility is the ultimate failsafe. VGA mode strips away all the high-end drivers, the hardware acceleration, the complex refresh rates. It forces the operating system to act like that basic motherboard BIOS again.
Oh, so it goes back to baby talk.
Exactly. It broadcasts a generic, universally recognized video signal. Practically every graphics card and monitor manufactured in the last 30 years contains the fallback hardware to understand standard VGA.
That is wild.
Yeah, so once you boot into that mode, you get your desktop back. It might look huge and clunky, the icons will be massive, but you can see your mouse well enough to safely uninstall the corrupted driver.
That makes perfect sense. Okay, let's push back a little bit and shift gears. What if the screen isn't entirely black, but just incredibly, frustratingly dim? Like you can barely make out the shapes of your open windows. You'd assume the monitor is dying, right?
Well, that requires you to separate the physical hardware from the operating system software behavior. A dim screen could indeed be a physical failure of the backlight.
Because LCDs don't make their own light.
Right. LCD liquid crystals do not emit their own light. They just act as tiny shutters. They rely on an array of LED lights shining from behind the panel. If that LED array starts to burn out or its power inverter fails, you might see uneven dark patches, or the entire screen might just look like it is in deep shadow.
And if it is the backlight, you're looking at a physical repair. You're opening the thing up or tossing it. But the sources suggest the operating system might just be messing with you.
Oh, it absolutely might be.
Right.
Operating systems are highly optimized for power efficiency now. So say you're using a laptop and you unplug the power adapter. The OS might instantly throttle the screen brightness by 50% to preserve the lithium-ion battery.
Which makes sense.
It does. Furthermore, many modern screens have ambient light sensors embedded right in the bezel. If a cloud passes over the sun outside your window and the room gets slightly darker, the operating system dynamically dims the backlight.
Wow, okay.
Yeah, it is the software trying to be ergonomically helpful, but if you don't realize it's an automated feature, it mimics a hardware failure perfectly.
Okay, so we've been blaming the hardware for being dead or dim, but let's assume we have power and we have a bright picture. Now we face a new problem. The image looks terrible, the text is fuzzy, the graphics are distorted, or the colors look completely wrong.
Right. If we connect this to the bigger picture, to understand why an image degrades so severely, you really have to understand the microscopic construction of an LCD. And that is entirely dictated by its native resolution.
Let's break that down. What exactly does native mean in this context?
So an LCD monitor is not a blank fluid canvas like an old tube TV. It is a rigid, unchangeable physical grid of tiny microscopic windows called pixels.
Yeah.
Let's say a monitor has exactly 1,920 horizontal pixels and 1,080 vertical pixels. That physical grid is permanently manufactured into the glass. It cannot change. If you want the image to be crystal clear, your operating system must send a digital signal that perfectly matches that physical grid.
1-to-1.
Exactly. One virtual pixel of digital data must map to exactly one physical pixel on the glass. That mathematical one-to-one ratio is the native resolution.
Here's where it gets really interesting. Because in the modern computing world, everyone wants massive high-resolution screens, right? The sources highlight a major dilemma with this. Let's say you go out, you drop some serious money, and you buy a beautiful 32-inch 4K monitor.
A great purchase.
You plug it in, you set your operating system perfectly to that 4K native resolution, so everything maps one-to-one, just like you said. But then you open a Word document, and the text is microscopic. Your desktop icons look like tiny little specks.
Yes.
The pixels are so densely packed that the interface is literally unreadable. So how do you fix that without ruining the crispness?
It is a pervasive frustration, particularly in enterprise environments where they upgrade everyone's monitors. The immediate instinct for a lot of users is to just go into the Windows display settings and pull the resolution slider down.
Right, because that makes things bigger.
They lower the resolution from 4K down to standard 1080p high definition, thinking if I send a lower resolution, the interface will get bigger.
And it does get bigger. But suddenly it looks like you are viewing your screen underwater. The crispness is completely destroyed. Why does lowering the resolution ruin the image quality so badly?
Because you are violating that physical grid we just talked about. Imagine trying to fit a 1,000-piece puzzle onto a table that was built exactly with individual grooves for a 500-piece puzzle.
Oh, that's a good analogy.
You can't just lay them down cleanly. You have to start overlapping pieces. When you send a 1080p signal to a 4K grid, the monitor's internal processor has to guess what to do with all the leftover physical pixels. This mathematical guessing game is called interpolation.
Interpolation. So the monitor is essentially making up data that isn't actually there.
Exactly. To fill the physical space, the monitor's algorithm averages the colors of the neighboring digital pixels and creates artificial transitional pixels to bridge the gap.
Wow.
It is essentially blurring the colors together to stretch the image. That interpolation creates the fuzzy, smeared text and the unreadable mess. You have completely bypassed the precision of the hardware.
Okay, so how do you solve the microscopic text problem without forcing the monitor to blur everything?
You never touch the resolution slider. You leave it locked at its native setting to preserve that perfect one-to-one pixel mapping. Instead, you use the operating system's UI scaling feature.
Scaling. Okay.
Yes, scaling is a purely software-driven solution. It tells the operating system, hey, keep the underlying mathematical grid perfect, but take the user interface elements, the text fonts, the window borders, the icons, and digitally redraw them using twice as many pixels.
Ah, so you weren't stretching the fabric. You were just using more threads to sew a larger letter on the exact same high-quality fabric.
Perfectly stated. Setting scaling to 200% gives you the physical size you need for readability while maintaining the absolute crispness of the native resolution. The hardware operates efficiently, and the software adapts the visual size.
That clarifies so much. It's such a common mistake. Now let's talk about color complications, because the sources bring up a frustrating scenario involving weird color tints. You turn your monitor on, and suddenly all your pristine white backgrounds look weirdly orange or washed out with a heavy blue tint. Again, the instinct is to assume the color processing board inside the monitor is fried.
And again, you might just be fighting the operating system's automated good intentions. Modern operating systems, Windows, Mac OS, your phone, they heavily feature night mode or night light settings.
Right.
These run on an automated clock. As your local time approaches sunset, the software intentionally shifts the color temperature of your display output, drastically reducing the emission of the blue light spectrum and boosting the warmer reds and oranges.
The idea being that harsh blue light suppresses melatonin and ruins your sleep cycle.
Precisely. From an ergonomic standpoint, it is a brilliant feature for a casual user just reading articles at 10 p.m.
But the sources point out a very specific professional reality where this helpful feature becomes an absolute disaster.
Yeah.
Imagine you are a graphic designer or a photographer or a video editor. You're staying up late to color correct a marketing photograph or a film scene. You need the skin tones and product colors to be mathematically perfect.
Right.
But unbeknownst to you, the operating system has quietly layered a warm orange filter over your entire digital workspace.
It fundamentally breaks the trust between the professional and the hardware. You are making permanent, potentially expensive creative decisions based on a digital lie.
Yeah, that's terrible.
You might spend hours adding blue to an image to counteract the warmth you're seeing, only to realize the next morning, when the nightlight turns off, that you have completely ruined the file. If color accuracy is any part of your workflow, Understanding how to permanently disable those automated color shifting profiles in the OS is just as critical as checking your cables.
Absolutely. Okay, so we've been blaming software for hiding our text and tinting our colors, but eventually the hardware itself actually starts to degrade. Let's talk about permanent physical artifacts, the hauntings and the dead zones.
What's fascinating here is the physical toll that rendering digital information takes on the materials inside the display.
Yeah, the sources describe burn-in or image sticking, and they use a highly recognizable example. I mean, we have all seen an airport monitor or a fast food menu screen where, even though an advertisement is currently playing, you can permanently see the faint, ghostly outline of an old flight schedule, or the word departures permanently etched into the background glass. What is physically happening to those pixels?
To understand that, you have to know how a liquid crystal actually functions. Between the glass layers of your monitor are millions of microscopic twisted molecules, the liquid crystals.
Okay.
When the monitor's logic board applies a specific voltage to a subpixel, those molecules physically untwist to allow a specific amount of light from the backlight to pass through a color filter.
So they're constantly moving. They act like microscopic Venetian blinds.
Exactly. Now imagine holding a heavy weight at arm's length for weeks on end. Your muscles would fatigue. The same principle applies to liquid crystals. If a monitor displays a static, unchanging image like the flight departure grid or a news channel ticker, those specific liquid crystals are held in the exact same twisted position under continuous voltage for thousands of hours. Eventually, the material suffers physical fatigue. It loses its elasticity.
Oh, wow.
Yeah, so when the voltage is finally removed, the crystals cannot fully snap back to their resting state. They get stuck partially open, allowing a faint trace of light through permanently. That is the ghost image.
Given that we all leave our taskbars and web browsers open in the exact same spots for hours every single day, how does modern technology fight against that fatigue?
Display engineers developed a brilliant, almost invisible software workaround called pixel shift. When enabled in the monitor's firmware, the display will routinely take the entire digital image and physically shift it just 1 or 2 pixels up, down, left, or right.
But I sit in front of a monitor all day, and I have never once seen the screen jump sideways.
That is the elegance of the design. It happens so slowly, and the shift is so microscopic that the human eye simply cannot perceive the movement. But at the physical level, it means a bright white line of a window border isn't resting on the exact same row of liquid crystals indefinitely.
It spreads the load.
Exactly. It distributes the voltage workload slightly to the neighboring pixels, giving the original row a fraction of a second to relax and preventing that permanent image sticking.
That is incredible engineering. But what if the ghost is already there? The sources mention a specific trick for LCD image sticking. If you have a faint ghost image, you can try displaying a pure, blinding white screen and leaving it on overnight. How does staring at a white screen fix a stuck crystal?
It acts as an aggressive physical reset. By displaying pure white at maximum brightness, you are sending maximum voltage across the entire physical grid simultaneously.
Okay.
You are forcing every single liquid crystal to fully untwist to its absolute limit. Doing this continuously for several hours can sometimes generate enough mechanical action to flesh out the stuck state, allowing the crystals to reset when the screen is finally turned off. It is essentially deep tissue massage for tired pixels.
Deep tissue massage for pixels. I love that. But what if it's not a faint ghost? What if it is a single, totally black dot right in the center of your spreadsheet and it just refuses to go away? It refuses to display any color at all. Is that a ghost too? Can you massage that out?
No, that is what we call a dead pixel, and it represents a catastrophic physical failure at the microscopic level. Behind every single pixel is a tiny transistor that acts as the gatekeeper for the voltage.
Oh, no.
Yeah. If one of those microscopic transistors blows out due to a manufacturing defect or physical trauma to the screen, that pixel goes dark permanently. The liquid crystal receives 0 voltage, so it remains in its resting, closed state, blocking all light.
And there is no software patch for a blown physical transistor.
None. The only resolution for a true dead pixel is replacing the entire liquid crystal panel, which usually means buying a whole new monitor.
But wait, before anyone rips their expensive monitor off the desk and throws it in the recycling bin and calls the manufacturer, there is a detail from the source material that I absolutely have to highlight because it is hilariously practical.
Please do.
Before you declare a pixel dead, take a microfiber rag and wipe the screen. Because half the time, that catastrophic, unfixable hardware failure is literally just a speck of dirt stuck to the anti-glare coating.
It is the ultimate lesson in IT troubleshooting, isn't it? Never bypass the simplest physical variables. The amount of diagnostic time, warranty shipping costs, and sheer frustration wasted on analyzing a speck of dust is astronomical. Start with the rag, then check the transistors.
Exactly. Always start with the rag. So what does this all mean when we move away from the desktop and push display technology to its absolute physical limits? The sources specifically scale up to discuss conference room projectors. We have all used them, but I don't think people realize the extreme physical environment going on inside those little ceiling boxes.
The physics inside a modern high-lumen projector are staggeringly intense. To throw a crisp image across a brightly lit boardroom and have it visible on a wall requires an immense amount of focused light. To achieve that, traditional projectors rely on high-pressure metal halide bulbs.
Okay.
The byproduct of that intense light generation is heat. The source material notes that the internal operating temperature of that metal halide bulb can reach a staggering 1,000 degrees Celsius.
Just to put that in perspective, 1,000 degrees Celsius is the temperature of flowing volcanic lava inside a plastic box hanging directly over your boss's head.
Which is exactly why the thermal management system is just as critical as the optical system. These projectors are packed with high-speed cooling fans and sensitive thermal relays. If those sensors detect that the airflow is restricted, they will instantly trigger an emergency shutdown to prevent the bulb from catastrophically melting the internal logic boards.
And this leads to a crucial operational rule outlined in the sources, the necessity of the graceful shutdown. We have all been in a meeting that runs long. The second it ends, someone just yanks the projector's power cord out of the wall so they can pack it up faster. Why is that such an expensive mistake?
Because you are completely disrupting the thermal management cycle. When you rip the power cord out, the cooling fans stop instantly. But that glass bulb is still radiating 1,000 degrees of heat.
Oh, right. It doesn't just instantly cool down.
No, not at all. Without the fans actively pushing cool air through the chassis, the ambient heat inside the plastic casing spikes massively. That trapped, radiating heat can literally warp the sensitive glass and plastic focusing lenses. More importantly, it drastically degrades the delicate filament inside the bulb itself.
So by saving 30 seconds of packing up time, you are cooking a replacement bulb that costs hundreds of dollars.
Exactly. A graceful shutdown means pressing the power button and letting the firmware take over. The lamp turns off, but the fans are programmed to run at maximum speed for several minutes to slowly and safely draw the heat away from the bulb. You have to let the machine finish its thermodynamic cycle.
That makes total sense.
And frankly, you need to remind your listeners to clean the external dust filters regularly, or the fans won't be able to pull cool air in to begin with.
Treat your lava lamps with respect, people. Let the fans spin. Okay, let's bring it back to the desktop for one final major meltdown scenario. You're working, and suddenly the screen starts violently flashing. Huge blocks of static, giant horizontal lines tearing across the display. It looks like the matrix is collapsing.
A severely artifacting or flickering screen is visually alarming, and it usually points to a severe breakdown in the data pipeline. As always, you verify the physical cables first. A single bent pin in a connector can cause massive signal degradation.
Right, check the hardware first.
If the cables are pristine, you might be looking at the logic board inside the monitor failing, or fragile liquid crystals breaking. But the sources highlight a highly specific software-level culprit that causes massive visual glitching.
And it is completely counterintuitive. It is a setting called hardware acceleration. There is a real irony here, because hardware acceleration is a setting explicitly designed by engineers to give you the fastest, highest quality screen updates.
In theory, yes. Instead of forcing the computer's central processor, the CPU, to draw every single pixel of your web browser, hardware acceleration offloads that rendering work to your dedicated graphics card or GPU. The GPU is custom built for drawing pixels, so it should be faster.
So why does the setting literally designed to make it go fast suddenly cause the screen to violently glitch out?
It is a classic case of component mismatch and driver bugs. Hardware acceleration requires a flawless high-speed baton pass between the web browser's software, the operating system's video drivers, and the physical silicon of the graphics card.
It's a complex chain.
Very complex. The GPU writes the image to a memory bank called a frame buffer. If there is a slight bug in the driver, or if the graphics card is slightly out of specification, it drops the baton during the handoff. The GPU processes the data out of order, and the monitor receives corrupted, fragmented frames. The screen aggressively flickers as it tries to display partial garbage data alongside real data.
And the fix is almost comically simple.
It is. You go into your browser or OS settings and just uncheck the box for hardware acceleration. By forcing the system to bypass the graphics card and do the rendering work the slower, more reliable way on the CPU, the image processing pipeline stabilizes instantly.
You literally fix the glitch by telling the computer to stop trying so hard.
Pretty much.
Before we wrap up, there's one last detail from the sources regarding cables. We use HDMI and DisplayPort for everything now, but they don't just carry video data.
Correct. They carry high-definition audio streams as well. If your monitor has built-in speakers and your screen looks pristine but there is zero sound, do not assume the speakers are blown. Because it is a separate data stream, the operating system treats it as a completely separate device.
So what do you do?
You must check your audio control panel in the OS to ensure the sound output is specifically routed to the HDMI or DisplayPort connection rather than, say, the headphone jack on the motherboard.
Simple, but easy to miss. Well, we have covered an incredible amount of ground today. We navigated the data handshakes of the black screen. We unraveled the puzzle logic of 4K scaling and interpolation. We massaged out liquid crystal ghosts. And we managed the thermodynamics of 1,000-degree projectors. You, the listener, are officially armed. You are a display detective.
You are no longer at the mercy of the hardware. But before we sign off, I want to leave you with one final thought drawn from the very last detail of the source material.
Oh, please do.
The material mentions that professional IT technicians use highly precise test patterns to evaluate the sharpness, geometry, and color representation of a failing screen. It is a strict grid of mathematically perfect lines and pure color blocks.
Right, to see exactly where the physical display is failing to meet the digital instruction.
Exactly. And this raises a really fascinating question to consider. Behind every seemingly perfect YouTube video you watch, behind every spreadsheet you analyze, or vivid video game environment you explore, there is an invisible underlying geometry of test patterns and precise pixels defining your digital reality.
It's all just math rendering light, constrained by physical limits.
Precisely. So the next time you are staring at a screen, I want you to wonder, how closely would the display you are looking at right now actually pass a technician's strict test pattern evaluation?
That's a great question.
How many invisible flaws? A slightly fatigued row of liquid crystals, a color temperature shifted just slightly too warm by the OS, a native resolution forced to interpolate a fraction off. How many of these invisible imperfections are we simply accepting in our daily digital windows?
It makes you realize how fragile the illusion really is. Because right up until the moment that screen goes black and the panic sets in, we just assume the window is perfectly clear. Thanks for joining us on this deep dive. We'll catch you next time.